Welcome to today's webinar. The topic today is 7 nonlinear material models in RFEM and their application. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, customer projects, technical content of the website, and so on. I will be the moderator today and also the presenter. My colleague Bastian Kuhn will answer your questions during the webinar. He is member of the product engineering team, especially for the timber add-on or timber design add-on. And he works also in the customer support team. You can ask questions via pressing that button with the question mark. Then you can enter your question in that field, press send, and Bastian will receive your question and he will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, at first I will introduce the nonlinear material models in RFEM 6. Then I present an example about the plastic steel calculation with the isotropic plastic material model. Then another example of a timber joint using the orthotropic plastic material model. And a third example, a nonlinear reinforced concrete calculation with the anisotropic damage material model. Let me introduce the material models. Where are linear material models? They are included in RFEM. That's the isotropic linear elastic model and the orthotropic linear elastic model. And with the nonlinear material behavior add-on, you have these 6 material models available. First, the isotropic plastic, then the isotropic nonlinear elastic, the orthotropic plastic Zaiwu, the anisotropic damage, isotropic damage, the orthotropic fabric, and then there's the soil models. Where are the soil models? Isotropic soil and isotropic rock. And for this material model is the geotechnical analysis add-on necessary. And for the first 6, the nonlinear material behavior add-on. Okay, for more information, you can press the button with the link here. Those are the first 2 nonlinear material models. There's the isotropic plastic material model. The difference to this material model, the isotropic nonlinear elastic model, is that after reloading, where is a deformation remaining, and this is not the case for this material model. So, okay, then there are 3 definition types. Standard. I will show all these definition types in the program. You can define equivalent stresses. In that case, with the material is yielding, and strain hardening modulus can also be defined with the bilinear definition type. And with the stress-strain diagram, you can define polygonal stress-strain relations. You can, you have the possibility to save and import such stress strain diagrams, and you have also an interface to Microsoft Excel. Okay, that's all to these two material models, at least in the presentation. I turn to the program to show an example. That's the first example, a column base with a plate and anchorage. The material is, sorry, can show that, steel S235 and 4 bolts here. I can show you the different loads. Pressure in that load case. Then let me show the transparent model. You can see the load, the tensile load, then a load in Y direction, X direction, then load in Y direction on the double, and load in X direction on the double. Then there are 31 load combinations, and those are included in the ultimate limit state. Ultimate limit state design situation type. So then let me show the forces or the stresses. First, maybe the deformation. So, and the surface stresses, equivalent stresses, Mises. You can see the maximum stress is for the steel S235, where maximum stress 235 Newton per square millimeters. You can set the diagram so that you can only see the overloading. Only parts of the structure are overloaded. It is better to see when you go to calculate and change the smoothing. Let me switch to constant on mesh elements, because those are the real stresses in the single elements. Okay. And if you move the button here, you can see the overloading, only these elements. But it's nevertheless difficult in my eyes to evaluate these results. In my opinion, it's better to use the plastic material model to evaluate such results. Let me do that. At first, I have to activate the nonlinear material add-on, or at first I can show you the available materials. Only these materials are available at the moment. So, and after activation of the nonlinear material behavior add-on, you can see all the other material models are available. At first, I show you the isotropic nonlinear elastic material model. You can see that diagram here, that what I showed in the PowerPoint slides. So let me change it to isotropic plastic. can see also that stress strain diagram with the remaining strain after unloading the structure. So basic or standard, then bilinear, and the stress strain diagram for polygonal stress strain diagrams. You can enter values here and define a diagram for your material. And you can use also the export import function to Excel if you want. So then let me change it back to the bilinear. You can set this factor to 0 or a different factor. Then basic. Okay, I have to enter the yield strength again. Okay. So, and that should be all. Okay. So then we have to recalculate all. That's now the plastic design. You can see the multi-core calculation of the load combinations. Let's wait a short moment. So now you can see the maximum stress is 235, as expected. You can see those are the same FE elements, but you have another option to evaluate that. That's the strain. And you can see the equivalent plastic strain when you check this. So, and you can see, just a moment, it's correct. The maximum strain is 1.5 promille. And the maximum strain according to Eurocode 3 is 5%. And that's what I would like to show you, that you can evaluate that result. You can also, what's the maximum plastics? That's only the plastics. Okay, that was the right one. Okay. So then, we can turn to the next material model. At first I would like to show you some sample projects on our website. That was a rectangular tensile membrane dome in France, where the RFEM 5 add-on was used for the nonlinear material behavior. And there's also another project. The target of, or the goal of this calculation was to compare the results of RFEM with another program results, and it was quite successful. Okay, let me continue with the slides. The next material model, orthotropic plastic, Saibu. It combines plastic and orthotropic properties, and you can use it, for example, for fiber reinforced plastic or wood or something like that. So, and it's also important is that the elastic range corresponds with the to the orthotropic linear elastic material model, and for the plastic range, the Tsai-Woo yield condition applies. I would like to show you also an example in RFEM. So let's jump to that example. Yeah, that should be, or I would like to model an oblique thrust joint. At the moment, it's only a surface or surfaces with surfaces made of steel. It doesn't matter. So I select all, right click, then surfaces, extrude into solid. Yeah, to another material. So timber, solid timber, C24 in that case. Okay. Then 140 millimeters. Apply. Okay. Now where's a solid made of timber, and let me change the material. Now we use the orthotropic plastic solids. Okay. So those are the parameters. I have to enter this one here. And you can also see the ultimate tensile strength, shear strength, and so on. That's the material model. That's the formula. Material values. Okay, that's all. So then I have to create a support. The lower surface should be supported. Double click on it. Support. New support. Supported in all directions. Okay. So then the loading. Surface, I enter a surface load. Uh, 1,500 kilonewton per square meters. That means approximately 46 kilonewton, a single load. Then local set is okay on that surface. Okay, the loading is complete. And now I have to define a surface release for these two surfaces. The connection between the horizontal beam and maybe the purlin. Okay, then surface release, right click, new surface release. I have to define the release type. I define a very small spring that we can calculate it, and in the set direction and nonlinearity, fixed if positive P set. So, okay. Yeah, and it's not fixed if the load is negative in set direction. I want to release the solid, the purlin, okay. So, and then the surfaces. surface and this surface. Okay. So, okay. Yeah, where it's necessary to release more surfaces, the neighbor surfaces and so on. That's the proposal of the program. I use action number 2. Okay. And now all is defined. So then we can calculate all. I have to correct anything. That's not the purlin in my eyes. That's the rafter. Yeah. The rafter and the horizontal beam. Let's calculate all. It's a nonlinear calculation on a solid. Yeah, but it's a small model. That's why the calculation is, takes not so much time. So then I select the solid basic stresses in sigma x direction. Maximum solid stress is 8.8 Newton per square millimeters. And if you want to evaluate the model in detail, you can use guide objects. In that case, for example, the clipping plane. So I activate it. So and you can go through the model and see the stresses. The maximum stress in x direction is here. That's quite clear. Okay, that was that model. You can use it, of course, for every other models made, for example, of timber and so on. So then we turn to the next material model, the anisotropic damage. You can use it for the nonlinear calculation of reinforced concrete. For members, surfaces, and solid. You can consider the tension stiffening between the cracks, and you can also consider long-term effects from creep and shrinkage. We will do that in the program. I turn to the next example. So that's a prepared timber concrete composite beam. Let me show you in the navigator data, in the navigator display. I will show you the solid model and then the surfaces, including thickness. You can see the distance is correct between the concrete plate and this horizontal beam, and both are connected with a rigid link. I double click on it, and there's also a line hinge defined with a spring constant for such timber concrete connection. So then the loading, self-weight, load case, and imposed load case, those are combined. And let's check the combination number 8, quasi permanent load combination. So I've already the calculation fulfilled, and you can see the linear calculation the result of the linear calculation is a deformation of 3.1 millimeters. We will remind that value later. So now we do the nonlinear calculation. I activate the nonlinear material behavior add-on. Okay. So, and I change the material for the concrete. What I forgot to mention, there's already a reinforcement defined. Let me double click on the surface. And there's already a surface reinforcement defined. And we will consider that reinforcement later in the static calculation. So at first we change the material model for the concrete. We use the anisotropic damage material model. We consider the tension stiffening. The other, we leave the other parameters. That's the stress strain diagram. Then the time dependent properties of concrete. We would like to consider creep and shrinkage. And this diagram is only for the graphical display. And the creep coefficient time diagram. We leave the material models, concrete settings, and so on. Okay. So then we change the material of the reinforcement. We change the material model from isotropic linear elastic to isotropic plastic. That's the same material model as before. So, and then we turn to the load cases and combinations. I select all load combinations and I add a structure modification. We would like to consider the surface reinforcement in the static calculation. That's why we do that. Okay. So, and now we can calculate only the combination number 8 to compare the results. With the linear calculation, we had a deformation of 3.1 millimeters. Now we have 3.8 millimeters. We have the nonlinear material model with a damage, but we strengthened the model with considering the surface reinforcement. Let me check the damage criteria, and you can see the damage factor. The highest damage factor is over the support, and also here in the middle of the fields. So let me turn back to the load cases and combinations, or I can do that also here. I add a comment. So without creeping, then I copy that combination and rename it to with creeping. So, and I changed the analysis type, creep and shrink it. I name it with creep and without creep. Okay, so and then let's calculate with the consideration of creeping and shrinkage. Calculate. So I check the deformation. And now you can see 9.1 millimeters with creep and without 3.8. And the linear calculation, where was the deformation? 3.1 millimeters. Okay. Then let's turn back to the PowerPoint slides. This is the material model, orthotropic fabric, nonlinear elastic surfaces. As the name says, the model represents an orthotropic fabric with nonlinear elasticity. It includes pre-stress and also lateral strain effects using a microstructure volume element model. Then the soil models, where are different isotropic soil plastic models, the modified hardening soil, modified more column, and the nonlinear elastic, and one for the isotropic rock plastic, the Höck Brown model. Yeah, and it's for geotechnical analysis. Yeah, and as I said at the beginning, there is no license required for the nonlinear material behavior add-on. When you click that link, you can see different webinars that we already present for the geotechnical analysis add-on. Let's turn back. Yeah, okay. That's also all to these two material models. Okay, that should be all for these three models. At the end, I have an additional hint to our online courses. RFEM 6 course for beginners, the Eurocode 2 course for the reinforced concrete design, then the Eurocode 3 course for the steel design, Eurocode 5 course for the timber design, the Eurocode 8 course for the earthquake design, and you can get more information when you scan the QR codes or click at the links here. You can get such a course for free when you submit your customer project. You can reach a form on our website by scanning the QR code or click at that link. The courses are valued at 199 to 399 euros. It's not much work for you, I promise. Then there are our free online services, for example, the Dlubal community. You can ask questions to our software, to our users, or to our employees. Then there's a GeoZone tool for the determination of snow, wind, and earthquake loads. You can use cross-section properties website. You can download 3D models as a template for your project. And of course, you can download the free trial version when you don't already use our programs. There are the programs RFEM 6, RStab 9, R-Section, and R-Wind available. And you can explore all our services when you click at the link or scan the QR code here. More information can you get on our website, dlubal.com. For example, the recorded webinars, the knowledge base articles, and you can ask our AI assistant, Mia, all the time. Okay, that should be all for today. I thank you for your attention. Thanks to Bastian Kuhn for answering the questions. I hope we meet each other in a future webinar. See you. Bye-bye.